last chapter in Unit 1, and we're going to go over trophic levels and interactions. So big thing, what's important here, primary producers, our photosynthesizers and chemosynthesizers, convert atmospheric carbon dioxide into glucose, and that is absorbed by our consumers, our heterotrophs. In between each level, we have energy loss. That's the conservation of energy, laws of conservation of energy. You have to know the first and the second. And then I want you to be able to see and visualize how food chains and food webs demonstrate these laws and demonstrate these trophic interactions. So trophic levels, they're feeding levels, and they're feeding levels based on the source of nutrients. What's your source? Are you making your own glucose like a producer would or an autotroph? They make their own organic carbon and they obtain it from their environment. So photosynthesizers obtain inorganic carbon dioxide from the atmosphere, and they convert it to organic carbon, glucose, and that is absorbed or eaten by consumers or heterotrophs. We don't make our own glucose. Last time I checked, we are not photosynthetic. We are consumers. Your dog, a consumer. Your pet snail, also a consumer. Your chia pet with the little grass on top, he's a producer. And we can show, this is a food chain. It shows both an aquatic and a terrestrial food chain, and it just shows each level of interaction. The producer that's being eaten by one consumer, eaten by one secondary consumer. We're going to talk about all those levels later. Food chains are not representative of what's actually happening in the environment. They're a very simplified version of these trophic levels. So this is what I already did that. Okay, so food chains show this flow of energy from one trophic level to the next. They are very simplified, especially if they're just showing one producer and one consumer. Ecosystems are not built this way. There are multiple producers. There are multiple consumers at every level. So I've shown a food web. It's basically an interlocking chain. This is even a very oversimplified version. These food webs and food chains can't be infinitely long because of the laws of conservation of energy. And you know, because you've already listened to this lecture in class, that energy is lost at each level, and that each time you convert energy from one form to the other, or it's passed on from one level to the next, we increase energy loss, which increases entropy. So they can't be infinitely long because it's just not efficient. And we're going to go over those laws at the end, and then I'm going to show this slide again, and you're going to be like, I feel great and I'm ready for the exam. So producers, they are the base of your food chain. They are the base of the food web because they are what's making our organic carbon, our sugar. So primary productivity is the rate at which carbon dioxide is fixed using sunlight to make organic carbon. The more water is available and the warmer it is, the more sunlight that's available, the more productivity that's going to occur. So this is why there's more primary productivity in a tropical rainforest than in the tundra, because there's more rain and there's more sunlight and it's warmer. So there's more photosynthesis that's going to occur. The more photosynthesis, the more productivity, the more sugar that's being made, the more carbon dioxide that's being converted into sugar. GPP is our gross primary productivity. That's the total amount of photosynthesis that's occurring in your ecosystem, or by that one producer. Your in that ecosystem, your NPP is your net primary productivity. So there are two big conversions that are happening in a plant, in a photosynthesizer. Photosynthesis is one of them, right? Converting atmospheric carbon dioxide into glucose, and then cellular respiration, taking that glucose and using it to make energy, ATP. When you do that, you lose carbon dioxide. It's a waste product. So plants are doing both. We only do cellular respiration. We eat their glucose. We eat plants to get their glucose, and then we use that glucose that we've eaten to make cellular energy so that we can go do activities with our bodies and with ourselves. So NPP is a primary producer, does photosynthesis and does cellular respiration. How much organic carbon is left over for the heterotrophs after they've used some of it for themselves to make energy. So they do photosynthesis so that they can use some of that glucose to make ATP. So they do a lot of photosynthesis so they can do a little bit of cellular respiration. And how much glucose is remaining? That's your NPP. Most plants, fortunately, capture more than they need. And so they store it, and when they store it, they get eaten. And then we use it. Hooray for us. There's two reactions. I said there was one reaction in photosynthesis, but there's actually another way that producers can make organic carbon, and that's chemosynthesis. So photosynthesis uses light as the catalyst to convert inorganic carbon into glucose, into sugar. Our big terrestrial producer, you guessed it, plants, and our main aquatic producer are phytoplankton. Chemosynthesis happens deep in our ocean, deep in our deep ocean basins at our ridges where there are hydrothermal vents or geothermal vents, and we're releasing hydrogen sulfide, and bacteria there do chemosynthesis. They use that sulfuric energy to convert inorganic carbon to organic carbon. It is fascinating. That's all I'm going to say about it, though. So consumers, what do? Well, now there's this organic carbon available, and they can eat it to make energy for themselves, to make ATP. So consumers eat either eat autotrophs that have made that energy for them, or they eat other consumers. So a primary consumer eats an autotroph. A secondary consumer eats a primary consumer. So you have a plant that converts inorganic carbon into organic carbon, into sugar. And then you have a rabbit eat that plant. That rabbit eating that plant, that rabbit is eating an autotroph. It is a primary consumer. And then a snake eats that rabbit. The snake gets its glucose from the rabbit, from eating the rabbit. It's a consumer. It's a secondary consumer because the primary consumer was the rabbit. The tertiary consumer eats the secondary consumer. You get it. You can build a chain on and on and on and on and on that way. However, energy transfer isn't perfect. So the first law of conservation of energy is that energy can't be created or destroyed, only converted. So producers absorb organic carbon dioxide and convert it to glucose. They've turned solar energy now into chemical energy. The second law is that during that conversion, some energy is lost. So when consumers eat producers and then absorb that energy, not all that energy is taken with them, isn't absorbed in it. They can't use it. And the number, that magic number that we're looking for, is 10%. 90% of the energy available is lost in the conversion. So when plants convert that solar energy into chemical energy, 90% of the solar energy is lost. And then when a caterpillar eats that plant, 90% of the energy that it has eaten is lost as heat. And so on and so forth. So then if you start off with like 1,000 kilograms of grass and the caterpillar eats that 1,000 kilograms, there will only be 100 kilograms available for, like, it will only have 100 kilograms. And then the bird that eats the caterpillar, when it absorbs all that 100 kilograms, there's only going to be 10 available. Like, it will only absorb 10 kilograms. And when the hawk eats that little bird, the 10 that it ate, only one of it will have. So 90% of energy is lost in between each trophic interaction, which is a lot. And this is just an average. So if you go out and you measure it, and people do, it's not going to always be like 90% hard, fast rule. Like, no, this is science. It's environmental science, and there's a lot of variation. Certain systems are more efficient than others. So if these food webs show flow of energy from one to the next, and there are these interlocking chains, they can't be infinitely long. That makes sense, because if you start with 1,000 and then the next 1,000 kilograms, the next level's max 100, then 10, then 1, you're going to have fewer and fewer amount of energy available at each level because so much of it is being lost. It was a hard and fast trophic levels.